So whenever we have algebraic expressions, so algebraic expressions can also be represented in terms of a query tree or a query tree notation. So what is a query tree? An internal data structure to represent a query. So whatever the query you have, you can represent this in the form of a query tree. For example, you apply a certain operator. So operator is there, and between two relations, so it forms a tree. So on every node we have a certain operator, and there are some relations which are involved, and that depends on whether those operators are unary or binary. The standard technique for estimating the work involved in executing the query, it helps you to determine the work which is being involved, how many operations are being involved. So if you want to compute the number of operations involved in a particular query, you can count the number of operations. And if you represent it in the form of a tree, then you will be easily understand that how many operations are involved, number one, and number two, what is the you can say the execution of those operators, which operator will be executed first, then the second and the third, so on and so forth. So nodes stand for operations like, as I told you earlier, it is either the select operator or the project operator, the join operator, division, renaming, union, intersection, so on and so forth. And the leaf nodes in the tree will be represented as base relations. So our tree gives a good idea and good understanding of what we are doing, because right now, because you are going through the relational algebra chapter for the first time, and it is always advisable to the students that in the early phase, whenever you write the algebraic expression, also make a tree, because tree gives you a good understanding of whether you have written a correct statement, or is there any problem in your statement. And that is further used in later on for the optimization process. As we know that what is an optimization always refers to either we go for the minima or the maxima, and in that case, whenever we say algebraic query optimization or a query optimization, it means that we want to execute that query in the less possible operations or the minimal possible operations. So whenever we have minimal possible operation, there is less cost involved. And if there is less cost involved, it means that less time is consumed. So whenever we are writing queries, we always look for the optimal queries. So that tree structure will really helpful in finding out the optimization process, or to understand the optimization algorithms, which is also an advanced topic which will be discovered, or which will be represented in chapter number 15 of this book, and which is not included in the first course. So here you can see the example of a tree. That example of a tree here you can see right now, that uh, let's suppose in the first phase you can see that which operator is involved, that is pi represent what? Pi represents the project operator, and the project operator actually tells us that how many attributes will be involved. So here P dot P number, P dot D number, E dot last name, E dot address, and E dot birth date. These attributes are involved in this particular expression. And here you can see a very small sign, but you can easily recognize that is a join operator. And that join operator is involved with the theta condition, which is equal to, where d dot manager ssn is equal to e dot ssn. Okay, and then you can see here again a join condition, that where d dot p dot d number is equal to d dot d number, and here that employee e is involved, and here there is a selection operator sigma is involved, which says that we are only interested to know the location about Stafford. So P dot location is equal to Stafford, and here that department is also involved. And now you can see in the reverse order. Okay, now let's see what we have selected. We have selected the location Stafford from the project. You can see here. So what we did, we apply the select operator, and then we applied a join condition with department, where p dot d number is equal to d dot d number. So we have the result over here. Whatever the result we have over here, we have a join condition with employee. So you can see department dot manager dot ssn is equal to e dot, and whatever the result we have these only interested in the values of these columns. So here we have the project operator. So in that manner, that tree is being built, and you can easily understand how those various operations are involved and in what sequence these operators can be introduced. So there are some other functions or operators which are also there when we talk about RA expression or relational algebraic expressions. And these additional operators are normally termed as aggregate functions or group functions. So in many queries, we need some sort of an aggregate functions like sum. We are interested in the sum of the values. We are sometimes interested in the average values, maximum or a minimum values. These functions are called group functions, or we call it aggregate functions. A type of request that cannot be expressed in the basic array is to be specify mathematical aggregate functions on collection of values from the database. For example, such functions include retrieving the average of total salary. Let's suppose we are only interested in the total salary of employees, or we are interested the average salary of employees, or we are interested in the maximum time duration of a project or a minimum time duration of the project. There we have to use those group function or the aggregate functions. Similarly, count is also such a function where we are interested to know, for example, how many employees are working in the project P1. So I need a count. So these functions normally give the single value. All other functions, all other operators like such as join, union, intersection, difference, selection, all these operators whenever applied on the relations gives the relation. But these operators whenever applied on the relations, they give a value. Okay, so that value might be the total value, that might be the minimum value, that value might be a count value. But we need these functions whenever we are writing such queries. So here you can see how it can be applied. So the function is normally represented with this italic f. So f, max salary of employee, retrieves the maximum salary of an employee relation. F, minimum salary, will retrieve the minimum salary value from the employee relation. Similarly, the sum of salary will retrieve the sum of the salary from the employee relation. And similarly, the count or the average function, whenever applied with the employee, will compute the number of employees and as well as the average salary of the employee. Let's suppose we have 12 employees and the average salary of employees is, let's suppose, 20K. So we can also use that grouping with aggregation as well. So we can combine these two things together. For example, the previous examples all summarize one or more attributes for a set of tuples. Maximum salary or a count, number of assets, and grouping can be combined with aggregate functions. For example, you want to know the number of employees in each department. So if you want to know the number of employees in each department, it means you group the data with respect to the department. Uh, You can also write, let's suppose in the same example in the company database, you might interested to apply those group function on projects, and you want to know how many employees are the count of employees working on each project. So how you write that query? So in that query, count is an aggregate function, and what you did, you make a group, and you make the grouping with respect to the projects you have. Similarly, that grouping can be done with respect to positions, that grouping might be done with respect to the departments, so on and so forth. So it all depends upon how you want to retrieve the data, or what type of query you have actually to retrieve that data. Here you can see some of the examples where we have three different queries, and you can see A, B, and C. And you can see in the A, you have the department number 5. So you are interested to know how many employees are working in department number 5, and what is the average salary of this department. So average salary of department number 5 is 33,250, and the average salary of department number 4 is this. Let's suppose you are interested in the department, and instead of counting the number of employees, you have counted the SSN. The same value will come because the SSN also represent the employees. So that is why you have the same values over here. And here you can see the total number of employees, that is 7, and plus 1 is 8. And the average salary of all these 8 employed will be 35,125. So in whatever manner, here you have used the department as a group, but you can also apply these queries with respect to projects as well, and you can see the results. So here you can also see the I just want to skip this slide because this refers to an SQL expression, so I don't want to confuse you with the SQL expression right now. So because we are just focusing on the RA expression. Although remember, whatever the RA expressions is, SQL actually is built upon RA, or relational calculus. So we have same operations over there, but we have various different symbols and operators which is actually represented in SQL. So do not get confused with that. Here, that is about recursive relationship. I think there is no need of it. I just want to skip this. Yes, this one is important. That is called outer join. The outer join operator. The outer join operator is very important to understand, because in a natural join or an equi join, tuples without matching are eliminated from the join result, because we only retrieve the tuples wherever the values are equal, but wherever the values are not equal are all eliminated. Number one. Tuples with null in the join attributes are also eliminated. Remember, so jahan pe null value hai, wherever we have that null value, that is also eliminated. So I just want to repeat this fact, that wherever you have the null uh, attributes, or we have, sorry, the null value in the joining attributes, those values are also eliminated from the result. And in other words, we can say it means that that information is not represented in the output. So we refer it the loss of information. So the outer join is one of the solution. So if you want to have that information, or if you think that information is also required in your case, then you can use the outer join operator. So it can be used when we want to keep all the tuples in R, or all those in S, or all those both in S relations, regardless of whether or not they have matched the tuples in the other relations or not. So there you are not only interested in the matched tuples, but you are also interested in the unmatched tuples. Sometimes you only want the unmatched tuples of S, that is the first case, or sometimes you are not, you are only interested in the matched tuple of R, this is the second case, and the third case is that you are interested in all unmatched tuples of R and S both. So that is the third case. So actually there are three types of outer joins. So the first one is called the left outer join. The left outer join, you can see with this bow symbol, you have these two parallel lines on the left hand side. So the left outer join operators keeps every tuple in the first or left R in R. So what will happen in when you apply this condition? All unmatched tuple of R will also will remain in the resultant relation, but not the unmatched relation of S. In the right outer join, you can see in the bow symbol, you have these two parallel lines on the right hand side of this bow symbol, which is a join symbol. It means that all unmatched tuple of S will be in the result, but no, unmatched tuple of R will not be in the resultant. And if you have the full outer join, so two parallel lines on the right hand side of the bow and two parallel lines on the left hand side of the bow. If you are using full outer, it means you are interested to find out in the result, you are interested in all unmatched tuple of R and S, all possible values. So that is the representation. So outer join operations can be used in various ways, and the outer join operation was developed to take the union of tuples from two relations if the relations are not type compatible. The operation will take the union of tuples in two relation R x and y and x and z that are partially compatible, meaning that only some of their attributes say x are type compatible, not necessarily that it is all type compatible. That is the condition we have with the outer join. So let's see some queries here. Now that is the last part of this chapter, which is very important, and I want you to concentrate on these queries so that we can give you the exercise later on and you can apply it yourself. Let's see the first query. The first query is retrieve the name and address of all employees who work for the research department. So remember, whenever you have a queries in your class or in your exercises or in your assignments or even in your exams, and later on when you are doing your professional work, I'll just giving you an idea how to resolve it. So whenever you have a query, and you have to write an expression. Now you have to do few things. Number one, read out the query sensibly and find out how many attributes are required or which attributes are required. Try to identify those attributes. Number one. Number two, try to identify how many relations are involved. Number two. Number three, try to find out, is there any condition which is involved? Or when I say condition, it can be a single condition or it can be multiple conditions. So on the third step, try to find out the number of conditions which are involved. So number four, which operators are do you think are relevant with this query? So once you have that idea, then you are in a good position to write the query. Now here in this query, the attributes which are they are referring are the name and address of all employees. That information is in the employee table. So that gives me the idea that is in the employee who work. But now we are referring to that they work in the research department. That information is another relation which is called department. It means that there are two relations involved. One is employee one is department. So if there are two relations involved and you want to extract information based on two relations, then it is definite that you have a joint condition. So instead of writing a single query, we break the query by using rename operator. And what we did, we are only interested in the research department. So we have a selection condition, that is sigma select d name is equal to research, and that information is in there in the department table. So the resultant will go into the research underscore department. And in the next step, there is a join between research underscore department and the employee, where d dot number is equal to d number dot employee, because these two relations have a relationship, and that relationship is actually with established with the d number, which is there in both employee relation and as well in the department relation. So whatever the result we have will go into, again it's a rename, research underscore employees, EMPS. And in the last step, in the research underscore employees, we applied the project operator, where we are interested in the name, and the name is divided into two attributes, f name and l name, and the address, and that information is going to the result. So in that manner, in that manner, we have the result of this algebraic expression. Now next, see the another query. Retrieve the name of employees who have no dependents. Now in that relation, in that conceptual model, or in the ER model of the company schema, we have discussed that dependent is actually an entity which is related with the employee, and we are only interested in those employees who have no dependents. So we are interested in all employees. So here the pi SSN means the project of employees. We are only interested in SSN. And then what we did is we take the ESSN from the dependent. So SSN from the employee to all employees, and ESSN from the dependent goes with the employees with dependents. And then what we did, we minus all employees with dependents, and here we apply the project operator, that is L name and F name, which is required. So we can easily have the information that these employees do not have the dependents. So that is the way in which we can write an algebraic expression. Okay, now here you can see the same query which we have seen in the previous slide Q1. Now it is represented in a single expression. So in the first step, I always say to my students or to the learners that you always prefer the breakup pattern, or use rename operator. But once you have a good idea of writing an expression, then write the complete expression. So if you want to have a single expression of Q1, that will be in this manner: pi f name and name address bracket sigma d name is equal to research, and then again the bracket department join d number dot dno is equal to employee. That same expression can also be represented in the form of a tree as well. So with with these examples, I just want to conclude the relational algebra chapter, and I hope that you have understood the concepts and will apply these concepts when I give you some home assignments. Thank you so much.